Hello everyone, welcome to NPTEL online course on electric vehicles. In today's interaction, let us discuss the next topic under vehicle dynamics, which is modeling and simulation of vehicle dynamics in Simulink. So, as most of you may be knowing, Simulink is a tool within MATLAB which is widely used for simulation of dynamic systems. So, it will be nice if we can model and simulate the vehicle dynamics also in Simulink. So, let us see how it can be done. So, when we see the total system of an let us say a battery electric vehicle, it consists of battery followed by power converter and motor, gear and transmission, and wheels of the vehicle. Battery also needs to support the power requirement of accessories such as air conditioner, heater, power steering, infotainments, and other things. So, when we want to model the total system, we have to model each of these subsystem individually. So, let us try to model the vehicle dynamics within a battery electric vehicle, or it can be same for even other vehicles such as fuel cell or ultra capacitor or ultra flywheel based EV, or a combination of many resources combined to drive a electric vehicle. So, this is the, you can say it is vehicle mechanical system. So, we are talking of driving profile, wheels, gears and transmission. So, we should be able to model all these things separately, and the models of this can be added later. So, as discussed, we have seen the diagram of a vehicle mechanical system, where an electric motor drives a fixed gear system which is connected to differential and to the wheels via a driving axle. So, this is basically fixed gear system. So, let us assume that the tractive effort on the wheels is Ft, which is driven at velocity v. So, if we know the basically radius of the wheels, we will be able to calculate the torque and angular velocity on the driving axle. Similarly, if we have knowledge of the gear ratio and the efficiency of gear, we can calculate the torque that is required on the motor shaft and the angular velocity of the motor shaft. So, using the understanding of the tractive effort that is required to drive a vehicle, we know that the motor has to support all resistive forces such as rolling resistance force, gradient force and aerodynamic force. So, this is the motor torque. If the vehicle needs to be accelerated, it has to also support the acceleration force, which is mass into dV by dt. So, if we substitute the resistive forces as a Fr, we can rewrite this equation as this equation. We have also seen the method of representing the resistive forces by means of ABC constants. So, in ABC constant, in addition to rolling resistance force, gradient force and aerodynamic force, we also consider the spinning losses forces as well. So, in some sense these constants and the force calculation using these constants is slightly more accurate compared to the previous case. So, we can also use ABC constant to represent Fr. So, we know that the angular velocity of axle is velocity of the vehicle divided by the radius of the vehicle. So, if we substitute velocity equal to omega axle into r in the dv by dt, we will get this equation. So, we will get a r term here. So, this r term can be multiplied by this r term. So, you will get a r square term here. Basically, if you do that, we will get a r square term here and this Fr will be multiplied by this r. So, if the r square is multiplied, this r square will be cancelled and m will be multiplied by r square. So, using this substitution with slightly reconfiguring this equation, we will get this kind of equation. So, the equation is a torque equation. So, here the equation is a kind of force equation, but this is a torque equation. So, this Mr represents inertia. So, this is inertia into d omega by dt equal to so it is very similar to that equation J d omega by dt equal to driving torque minus load torque. So, this is equation we use for mechanical system. So, it is very similar equation. So, this equation can be further modified as this. So, we can substitute Fr into r and we will get Tr. So, we can say the torque due to resistive forces can be now termed as Tr. So, this equation becomes this. So, basically here it was kind of Fr into r and which we will rewrite at this using this substitution. So, if we write this equation in terms of d omega xl by dt, we can move the inertia as 1 by inertia into the difference of driving and resistive torques. This equation can be now integrated. So that we can calculate the value of omega xl. So, omega xl will be integration of the Stoichkov equation into dt. So, if we want to get a transfer function in S domain with respect to this time equation, we can do the Laplace transformation and we can get a transfer function with respect to this equation. So, it will be, so the integration of dt will be 1 by s, and this equation will become. So, on the left hand side we have omega xl. So, it will be also nice if we can substitute the motoring torque also as function of T XL. So, we know that Tm is 1 by g eta g of T XL. So, if you substitute this here, we will get this equation. So, this is kind of equation in the driving axle. So, generally in a driving profile, so if we look for driving profiles, these are basically curves of v of t. So, let us use this transfer function and all these relations. So, all things can be related to velocity. So, the more exact version can be done by using ABC constants. So, we are relating here kind of the velocity profile and the. So, the input to the system is torque of the motor and output is velocity. So, we will be able to put all this together such that we will be able to do the modeling the way we require. So, if some of you may be accustomed to Simulink tool of MATLAB, it uses very simple terms such as addition, so this is addition, this is addition subtraction block, this is a multiplication block, and this triangle shaped is a kind of gain blocks, and this kind of trigonometric block sine function. So, using very simple blocks of Simulink, we can able to model these equations. So, how we can do that? Let us see. So, we know that the input to the system is the motoring torque. So, the motoring torque has to be first converted to the axial torque. So, if we multiply g eta g to Tm, we get basically T axial at the output of it. So, T axial has to be subtracted by the equivalent torque proportional to the resistive forces. So, we need to calculate Tr here. So, what is Tr? So, Tr is a product of Fr into R. And what is Fr? Fr is basically A plus Bv plus Cv square plus mg sin theta. So, another input to this system is the slope angle. So, if we know the slope, we can define the angle, and it can be multiplied by sine function to get basically here sin theta, and if it is multiplied by mg, we get basically here Fg, the force due to gradient, and this is the force due to A constant, B constant and C constant. So, for the calculation of this resistive force, we need velocity information. So, how to get the velocity information? We can do that once we know the acceleration torque. So, we know T XL minus Tr is nothing but T acceleration. So, this is basically T acceleration. So, once T acceleration is known, we can multiply this T acceleration with the equivalent inertia of the system. So, we know that it is m r square plus g square eta g by j m. So, if you divide this t acceleration by this equivalent inertia, basically here we will get a term which is, so this term is d by dt of omega axle. So, this is angular acceleration. So, once we have the angular acceleration, if we integrate this angular acceleration, we will get the angular velocity itself. So, here the output is omega axle. So, you can see that it is omega axle. So, inputs of the system is, one is T m, two is angle. One of the outputs of the system is omega axle. So, once the omega axle is known, and if we have the information of the radius of the wheels, we can multiply omega axle into r by means of a gain, and we can get velocity. So, this is first output, is second output. So, now we have the velocity information. So, once you have the velocity information, we can use it to calculate BV force, CV square force. So, here V into V, it will create a V square. We can multiply by C to get the CV square. On the motoring side, we may like to know the angular velocity of the driving shaft. So, if omega axle is multiplied by g, we can get omega m, which is the angular velocity of the driving shaft of the motor. So, we have three outputs, omega axle, velocity and omega m. Inputs are T m and slope angle. So, you can see it is a very simple way of representing the vehicle mechanical system in Simulink. So, once we do this, we can create a subsystem. If we combine them into a common block, we will have two inputs to the block, T m and slope angle, and three outputs, omega axle, velocity and omega m. So, let us see how it looks. So, if we do the subsystem generation for the system we have just talked, we can create this subsystem where these are the outputs, and we can also take resistive torque as one of the outputs. Input is motoring torque and slope angle. So, this kind of block can be used to connect with the motor control blocks. So, generally electrical drives basically the control of electrical motor and the motor itself, and their modeling is done in Simulink, and it will be very useful to connect the vehicle dynamic system to the electric drive system using this kind of blocks. So, we will see and do that exercise somewhere later in the course. So, we have seen that for a variable input tractive effort, generally there are three regions of operation. So, we have constant torque mode, constant power mode and constant speed mode. So, these modes are are based on the vehicle speed. So, when the vehicle speed is between 0 and V rated, we say it is a constant torque region. So, and together with Tm equal to T rated. So, this together is constant torque region. Similarly, when the velocity is between V rated and V max, and torque is integral proportional to velocity, this region is basically constant power region, and when the velocity is greater than V max, we say it is constant speed region. So, if we want to incorporate all these features in this block, we have to incorporate these conditions in the block. So, we have already seen how this vehicle mechanical system can be made. Now, to incorporate these conditions and obtaining the different regions of operation, we need to vary the torque input to the system. So, we know that the motoring torque is T rated in constant torque region, it is 1 by V in the constant power region, and it is only equal to losses of the system when we are operating in constant speed region. So, this can be done using some kind of selection or comparison of speeds. So, let us take the angular velocity of omega m for doing that comparison. So, when omega m is less than omega m rated, this block, which is basically switch block in a MATLAB Simulink, it will tell that if the omega, so this input is coming to this block. So, if omega of the system at current time simulation is less than omega m rated, the torque input to the system will be T rated. So, this selection is based on the current angular velocity of the motor, and this block will also tell that if the omega m is greater than omega m rated, then use the value which is coming from here. So, this value now we have to see how. So, this value of torque may be of constant power region or constant speed region. So, these two blocks help us to do that. So, again this omega input is coming to this block also. So, when the omega m is greater than omega m rated, this block or this switch block, basically this is another switch block, becomes active, and it will tell the torque input to the system will be P rated into 1 by omega. So, this is a reciprocal function 1 by u. So, P rated into 1 by u of omega m will now go as the torque input to the machine. So, if this, so first is this block. So, let us say, so this block will be active. So, this is basically block 1, which is this. So, constant power region is basically this block or this switch block basically, and this is constant speed block. So, first in constant torque mode based on speed feedback, T rated will be selected, when the omega m is greater than omega m rated, P rated by omega m will be selected as torque input to your system, and when the omega m is greater than omega m max, this switch will be selected, losses. So, here we only support losses. So, this can be this kind of intelligence can be incorporated, and we can get all these three regions of operation. So, let us see the results pertaining to this simulation block. So, let us take a sample vehicle data. So, the rating of the machine is 80 kilowatt. The torque rating of the motor is 250 Newton meter. The maximum speed of the vehicle in kilometer per second is 150. So, it will be 41.6 meter per second. Gear ratio around 8, radius 0.3, mass of around 1500, efficiency of 0.97. So, let us try to add this data to the Simulink blocks we have discussed and see what kind of results we get. So, this is basically torque with respect to time. So, this is Tm, torque of the motor, and this is Pm of the motor at different instants of time and with respect to speed. So, this is basically time. This is basically torque in Newton meter, and this is basically power in watts. So, you can say it is 8 into 10⁴. So, it is roughly. So, this so we can see that we have three regions of operation. So, this region is constant torque region. So, here the torque is constant equal to T rated. So, 250 Newton meter, in constant torque region we know that the power increases linearly from 0 kilowatt to 80 kilowatt. So, this is P rated equal to 80 kilowatt. You can see 8 into 10⁴. So, this system has a pretty wide constant power region. So, this in this region the torque droops as a function of speed, and when we reach the V max, so torque will be reduced only to support losses. So, this region is constant speed. So, you can see that it is very easy to do the mechanical block simulation in Simulink, and we can get very nice results. So, in this graph in addition to torque and power as a function of time, so we can also plot the velocity of the vehicle. So, it increases from 0 to 40, 41 basically this is 41 meter per second. So, this is V max. So, we get V max of 41 meter per second when we reach constant speed mode. So, the rating of the will be somewhere, I think it will be 15 meter per second, maybe the rated velocity of the vehicle, and it will go to 41 meter per second in constant speed region. So, this is kmph max, this is V max. So, V rated maybe in the order of 15 meter per second. So, we can do simple simulation and get the results of V of t, torque with respect to time, power with respect to time. So, we have also discussed the driving cycle of an electric vehicle. So, when a mechanical system is driven on a driving cycle, we can use that simulation for calculating range. So, let us see how we can incorporate the driving cycle to the mechanical block. So, there is basically a block which is known as signal builder in Simulink, which is very useful block, and it can be used to generate any kind of driving cycle profile of velocity versus time. So, this block is signal builder, can be seen here. So, here basically, so these are different points. So, these points can be selected in a xy graph. So, we can say that the x axis is time in seconds. So, the signal builders gives any signal with respect to time. So, time in seconds can be, so these values can be put. So, basically these are kind of xy coordinates. So, this is basically T1 V1, this is T2 V2, T3 V3, T4 V4 and T5 V5. So, all these coordinates can be selected in this signal builder, and we can get any driving cycle profile we need. So, we have seen that this SAE J227 driving cycle profile is very similar to this. So, we have a acceleration period. So, this is basically acceleration period. This is constant velocity period. This is deceleration period. This is a kind of idling period. So, let us try to see the simulation of mechanical system when the input is kind of driving cycles. So, there are some results. So, let us say if we use a driving cycle like this, where we have a acceleration from 0 to 15 seconds. So, the vehicle is accelerated from 0 to basically 30 meter per second in 15 seconds, and then we have a constant speed of 30 meter per second from 15 to 20 seconds. Then we have a deceleration from 30 meter per second to 0 from 20 to 25, and then we have a 0 speed from 25 to 30. So, if we try to see the results, so these are basically the results of the motoring side. So, basically this is omega m, this is T m, this is P m, and this is the energy required. So, this is delta energy. So, how we get energy? Basically, so energy is very simple. So, energy can be calculated as 1 by S of P. So, if you just integrate, we can get the energy value. So, once we have the power value, getting the energy is very easy. So, you can see that so we are accelerating from 0 to 30, 0 to 15 seconds, but you can see that, so this is acceleration period, but a part of it is constant torque and part of it is constant power. So, you can also see that when the speed of the vehicle becomes constant, the torque also becomes constant to a lower value and power also becomes constant, since power is torque into omega m. And you can see that the rise of energy required increases here, and it increases very slowly because we do not have to supply the accelerating torque in constant speed region. So, this is constant speed region or constant velocity mode. So, when we are decelerating from again, so we are accelerating from basically 30 meter per second to 0. We also have to go to the same mode. So, initially it will enter constant power mode. So, this is basically again constant power mode and this is constant torque mode. So, since the deceleration time is lesser, this period is also lesser. Here the acceleration time is more. So, we have a bigger constant torque and constant power modes. So, if you see the power plot, we can say that so we are power is increasing linearly in constant torque region, it becomes constant in constant power region, it becomes very less only to support losses in constant speed region, it becomes negative. So, this is negative value of power. So, this is negative P rated. So, here we can see that when the power input to the system is negative, it means we are regenerating. So, if that option is there in the electric vehicle to absorb power from the wheels to decelerate the vehicle, we can add energy to the battery. So, you can see that so this is the del energy. So, it increases up to here and then it decreases. Decreases means now the battery is getting charged. So, if we would operated the vehicle up to here, the delta energy will be like this. But if we operate even in the deceleration mode, the del E required will be less. So, you can say that some energy what we have given for accelerating and constant speed region is recovered during deceleration. So, basically this is the regenerative braking. So, where power becomes negative and energy is absorbed by the battery. So, this is deceleration and 0 speed, and here it is basically constant speed, acceleration, constant speed, deceleration and 0 speed. So, let us try to see results for a different profile. So, here same graph, so the maximum speed is 30 meter per second, but now we are accelerating only for 10 seconds, but we are accelerating for 10 seconds and we are decelerating also for 10 seconds, and the constant speed region is 10 to 15 seconds. So, we will see what kind of results we get. So, again similar graphs, constant torque, constant power, constant speed, constant power with negative power, constant torque, and basically again losses. So, we can see that the energy requirement increases, but we are able to recover almost all the energy. So, the del E required will be very small, only is pertaining to losses of the system and the power required to support this constant speed mode. So, you can see that almost everything is recovered. Again, if we try to see a system where the acceleration is only for 5 seconds, but the deceleration is greater now. So, deceleration is for 10 seconds and the acceleration is for 5 seconds. We have a constant speed mode from 5 to 15. So, what will happen here? So, in this mode you can see that the acceleration is only for this period, but the deceleration is for wider period. So, here we are able to recover some energy from the wheels, and so the net energy is negative. So, we are able to charge a battery actually if we operate this kind of driving profiles. So, one thing is very clear from this simulation results is that if we know the battery capacity and let us say we have to move from one place to another, we can choose the driving profile in such a way that we can able to get maximum range. So, if we have periods of acceleration deceleration in this fashion, we may not lose any energy of the battery, rather we gain something out of it. So, this kind of simulation of driving profiles, mechanical systems, and the suppression of constant torque, constant power and constant speed mode within those vehicle mechanical blocks will be very useful for a vehicle designer. So, these kind of simulations are generally used by designers to choose the type of battery, the type of motor, the ratings of the motor, and all the subsystems within a electric vehicle. So, that is all in this last topic of vehicle dynamics. So, we have covered the vehicle dynamics topic. So, these were the topics and we have covered the last topic today. So, thank you for listening the lecture.